For Calculus Notes 2.4, we're going to be working with the imaginary unit I to write complex numbers. So far, we've just been working in the real numbers, and now we're going to work and bump up to the complex numbers. Complex numbers are composed of real numbers and imaginary numbers. And we have in this unit that I, which is equal to the square root of -1, is what we call the imaginary unit, so that I squared is -1. And so each complex number can be written in standard form, a plus bi, where a is your real part, and the bi is your imaginary part. Again, the square root of -1 is I. So we're going to pretty much treat I like we would an x in terms of a variable as we work through this. And so in this first equation, you're just going to be you're adding. So we have 9 plus 2i plus 1 minus 6i. And so you're going to get 10 minus 4i. And in the second one, when you distribute the negative, you have 4i plus 3 plus 5i. And then we're adding, so just drop the parentheses. And you're just collecting like terms. So we have a 4i, a 6i, a 5i, and a minus 6i. So we get 3i. And then we have 3 and 2, which is plus 5, but we can't leave it in that form. You need to write it in standard form, so it needs to be 5 plus 3i. And then this last one, 5 minus I plus, you can just drop the parentheses because we're adding that. But on the next one, you have to negate both of them, distribute that negative, so minus 12 minus 3i. And then let's go ahead and the 5 and the 3 and the minus 12 combine to be a -4. And then we have the minus I, the plus 4i, and the minus 3i. Ends up just being 0. So this ends up just being a real number when you end up adding those. All right. So addition and subtraction, you're just collecting like terms, treating it like it's an x. Perform the multiplication. Now when we get here, we're going to get I squareds. And for every I squared, you have to replace it with -1. You can't leave I to a higher power than 1 when you write your final answer. It could only be I to the first. Or in the case of this last example, if it comes out to just be a real number and there's no I at all. So we're going to be replacing anytime we see an I squared with -1. So we multiply this out just like we would if it was 8x and 3x. So 8i times 4, 32i, minus 3 times 8 is 24, but you have an I squared. And I squared is -1. So you end up taking that -24 times a -1, which is plus 24. And so we put the real part first and the imaginary part second. And so we will write that 24 plus 32i. Part B here, we FOIL it out just like we would if these were with x. So 3 times 5 is 15, 3 times 4i is 12i, minus I times 5 is minus 5i, minus I times 4i is a minus 4i squared. So then we have 15 plus 7i, and we have that minus 4 times a -1, which is plus 4. So we get 19 plus 7i. And as you get going on that, you don't have to show the step where you write I squared as -1, but I wanted to on the first few problems here just to emphasize that's what's happening. Now, in this next one, this means, notice, copy the original problem down and then have equals as you work down. 5 minus 3i times 5 minus 3i. And so, but it's that when you square a binomial, you get a trinomial. I cannot emphasize that. The error that people make is they just get 25 minus 9i squared, and that's wrong. You've got to square it, multiply and double it. You've got to do the whole FOILing process. You end up with 25, that minus 15i minus 15i plus 9i squared. And so you have 25 minus 30i, and the I squared is a negative 1, so we'll just make that a minus 9. And so you end up with 16 minus 30i. Okay, in this next example, this was supposed to be 3 plus I. Sorry about that. Multiply each complex number by its complex conjugate. And so complex conjugates, if you have A plus B, I, the complex conjugate, is A minus BI. The first term stays with the same sign, but the imaginary part has to switch signs. And so 3 plus I, the conjugate is leave 3 with the same sign, but change the imaginary part and have it have an opposite sign. And then as you multiply this out, you get 9 minus 3i plus 3i and a minus I squared. And with complex conjugates, that always happens where the middle two terms are opposite. It's that A plus B times A minus B where the middle two terms cancel always. So we have 9 minus I squared, but I squared is a negative 1. So you get 9 plus 1 minus the negative 1's plus 1, and you get a value of 10. And you should expect that when you multiply complex conjugates, that you have, you end up with just a real number. And we're going to use that in this next upcoming example to help simplify a quotient. All right, so if I have 5 minus 4i, then multiply by 5 plus 4i. Notice I'm writing that and then an equal to sign, communication. So we get 25. And then if you can anticipate it, the middle two terms are going to cancel. So we get minus 16i squared. But that I squared is a negative 1, so you get 25 plus 16. And you end up with 41. In the next example, write the quotient in standard form. Standard form is going to be the A plus BI. You have to separate out the real from the imaginary. And when you have a quotient, the key to doing this, and you have to just memorize, this is the process that you do, is you multiply by the complex conjugate of the denominator, both the top and the bottom. That way you're really multiplying by 1, and you won't change the value. So I'm going to just bring this down here. Well, I can just work with it from right there. So on this next line, I'm going to put equals. And in the numerator, you have to FOIL that out. So you get a 15 minus 12i minus 10i plus 8i squared. And then in the denominator, we just practice multiplying complex conjugates. The power of this is that it gets it to be a real number, which is what we need. And so the middle two terms cancel, so it's just 25, and you get a minus 16i squared, which is that 25 plus 16. So that denominator is going to be 41. And in the numerator, the 8i squared is a negative 8, and 15 and a negative 8 is 7. And then we have minus 22i. Now, you can't leave it in that form. You have to separate out when it says standard form into the real and the imaginary. So we are going to write it 7 over 41 minus, and we're going to write it 22 with a flat fraction bar 41, and that I is going to be centered with that fraction, and it's going to look like that. So there is your complex number in standard form. Again, the 8 times the I squared is -1, was a -8. 15 minus 8 was 7, and collected like terms. And that's the form you have to write it in. You can't leave it in the step before because it's not in standard form. So you've got to get down to that answer. So remember, the square root of -1 is I, so that's going to allow us to simplify. However, there's something kind of special about part B that we need to know, but we'll do that when we get there. So being able to simplify this, you need to be able to simplify radicals without using your calculator. And what I like to do is just, you should actually have a couple ways. And one is just know what is the largest perfect square that goes in a number. And the other is doing what I call a ladder kind of thing to simplify. So I'm going to show both. So start by writing the original problem down. And in 27, hopefully you know that 9 is that largest perfect square that goes into it. And so I can break this up into the square root of -1 times, I want that square root of 9 because the square root of 9 is 3, and I have a leftover root 3. And so the square root of -1 is I, the square root of 9 is 3, and then we have this root 3. So I would write it 3I root 3, and we have simplified it. So that square root of -1 is going to come out and just be I. Be careful. If you put your I behind, it's really easy to have that square root go a little too long and have it appear that the I is underneath the radical. And if you do that, you won't get credit. That's why in some instances I put the I in front of the radical. Okay, I was going to show you just another method, just using 27 as positive. I call this the ladder method. You just start with what is the smallest prime number that goes into 27, which is 3. And 3 goes in there 9 times, and you keep on taking prime numbers into that until you get to the bottom, and it's a prime number. And then for the square root, for every pair of numbers, 1 goes on the outside. So the square root of 27, there's a pair of 3, so 1 goes on the outside, and the leftovers go underneath the radical and get multiplied. So the square root of 27 is 3 root 3. But then since it was the negative square root of 27, there's an I in it. But just, I don't know if you've seen that before, but that is a method when numbers get larger and you're not quite sure what the largest perfect square is that goes into it. Okay, now part B, the square root of A times the square root of B is the square root of AB only when A and B are greater than or equal to 0. And so you will have an error if you multiply these two and get a positive underneath the radical. That won't work because it's a -15 and -3. You can't multiply both of those if they're both negative. And so what we need to do is write this as I times the square root of 15 times I times the square root of 3, treating that square root of -1 as I. So that produces an I squared. Now they're both positive, so I can go ahead and multiply those out and get the square root of 45. And now the I squared is going to be a -1. So I have the square root of, or the opposite of the square root of 45, a negative square root of 45. And then 45, I could do the ladder method if I wanted to. 3 goes into there 15 times, 3 goes into there 5. But I also know it's just 9 times 5, so it's square root of 9 is 3. And you get a -3 square roots of 5. Otherwise, there's a pair of 3s, so 1 goes on the outside and the 5 stays underneath the radical. All right, on the next one, when you square it, multiply and double it type of thing, you can do that. Just be careful. You probably want to first write the square root of -5 as I root 5. And I'm going to just go ahead and FOIL that out. but I'm going to change the square root of negative 5 to be I root 5 before I get started. So distributing my negative 2, I have a positive 4 minus 2I root 5. Distributing the I root 5, I have a negative 2I root 5. And then I root 5 times I root 5. I times I is I squared, and root 5 times root 5 is 5. So you get I squared times 5, which is going to be a negative 1 times 5. And the middle two terms are like terms, so you have 4I root 5. And then it's that negative 1 times 5. So we have 4 minus 5 is a negative 1 minus 4I root 5. Notice how I work down the page equals at the beginning of each line, full complete expressions. And then in example 6, if you start trying to solve this and you try factoring, it's not going to work all that well. And perhaps you'll remember the discriminant is b squared minus 4ac. And if you take that 5 squared minus 4 times 7 times 2, and so we've got 28, minus 56 is a minus 31, which is negative. That means that there are two imaginary solutions, or complex, I should say, or complex solutions. And so when that discriminant is negative, we expect that you're going to have an I in your answer when we're working in the complex field. And we're going to go ahead and use the quadratic formula, which is a negative b plus or minus the square root of b squared minus 4ac all over 2a. And my a value is 7, my b value is 5, and my c value is 2. So notice I'm going to put x equals, because that's what we're solving for. So a negative 5 plus or minus the square root of 25 minus 4 times a times c all over that 2 times a. So a negative 5 plus or minus the square root of, and we had it already worked out. That comes out to a negative 31 all over 14. And so we would be looking at 31 and trying to prime factor it, but 31 happens to be prime. So that's going to be negative 5 plus or minus I root 31 all over 14. But in standard form, that's a negative 5/14. And I would write it the square root of 31 over 14 and the I centered. Now, when you're solving equations like that, they don't always mandate that you put it in standard form like they do when you are just doing operations on complex numbers. So I wouldn't be surprised if the textbook doesn't give it to you the first way. So the difference is here you're solving an equation and it happened to come out that the solution was complex, versus when you are working with imaginary numbers, then they're going to want the final answer. When you're doing operations, multiplying, adding, subtracting, they're going to want this final answer in standard form. So there's just a little bit of the difference on that.